to share screen and let's chat a little.
Okay. I can't share my screen. Okay.
Oh yes, yes. Let me fix it quickly. Everyone. So Ellison is co-host. Sibel is co-host. Lola make co-host. Yes. Adam make co-host. Yes. Okay. Yeah. And are you sharing one window or the whole display?
Oh, okay. Do you see this figure?
Yes, I do. Very good.
Okay. It's not letting me drag this out of the way. I could not open this one. I don't know why.
You cannot?
Yeah.
Can you? I will request remote control and yeah, thank you. Is anything is still running right now?
No, I don't think anything is running.
No, it's still running. You see, there is a dynamics going on.
Oh.
So it's not allowing you to do things because it's still running. But
and this is 4.5 since the beginning.
And then run later. If you do, you can stop it while we are discussing and then you rerun it once again. Is it okay?
Yeah, sure.
Let's do Control C. And so in order to explore this piece of code, can you bring back the command window? Or I think I can do it myself. This. States. So it does work. It generates spectra, right?
Mm-hmm.
So there are two questions. One to get basic idea how it works, and second to set up parameters. Right now, where are okay, here are the texts of the scripts. So what is this factor 0.0074? Do you have an idea?
No, I don't know.
0074. It's not what I thought. Okay. So to my understanding, the lines 49 and 52 are the most important. So the values of the parameters. By manipulating values of parameters for these equations, one can get different spectra, and one can select such parameters to make this to reproduce emission of your copper spectra. So the DE of must be your homoloma gap. So if you can start playing with it. How do you have a specific complex in mind, and do you have the value of homoloma offset or transition energy, lowest transition?
For the ground state?
Yes, for the ground state, transition energy from TDDFT or homoloma energy offset.
I have to look through. I have to look. I will have to look for one of my structures.
Okay.
I don't exactly have it opened.
Is it something like 1.8, about 2 electron volts? Would it be correct?
1 point. I really don't remember. It's not up to 2.
About 2?
It's not up to 2, but it's about 1 point something. I don't really remember.
Well, you can figure it out later, but so here the offset is said to be 0.2 electron volts. So it is much smaller than you need. And this number is because we are doing it in atomic units. For example, if your transition energy is 1.9 electron volts, right? The energy of set in atomic units will be 0.07. So let's go to the beginning. And so the mutual positions of the equilibrium, let's save and run, and then maybe keep analyzing further. So going here, we use this WP Marcus B. Busy. So right now it doesn't show second parabola because it is offset by a much bigger value. So maybe one needs to change the axis by about 10 times bigger. So let's go to the script and go inside the loop. So inside the loop, there should be command axis, which will control the range. Interesting. I did not see it, but we'll figure it out. Maybe let's go from the very beginning and then use this search.
Yeah, I was going to think of MATLAB how we control it.
Axis. Minus 0.8, 0.05. Let's check if it is what is going on.
Yeah, it is, I think. Yeah.
So let's we need, since we are using 10 times bigger offset this way. Okay. Let's try to run it once again. Figure and rerun. Busy. I have zero. It's too far. But now we see two parabolas. Their equilibrium position is offset, and it will determine the spectra. And since we are looking onto the dynamics, not dynamics, but actual Frank-Condon overlaps and eigenstates, we can stop it in the middle. Control C, and run this states eigen. So it looks like no, something is not good. Let's open this states eigen and analyze. Okay. The calculation of spectrum is going on, uses energies in electron volts, and the E range is in Hartree units. So we can. Okay. I think I'm getting what is going on. Better, much better. Okay, so here are results for your emission spectrum, assuming that all parameters are correct. So although by if one neglects vibrational subset, the peak should be only at 1.9 electron volts. Here it has additional shoulder protruding up to 2.3 electron volts. Do you see it?
Yeah, I see it.
Okay. And the reason why it was not working before is that why it was not working before, because we skipped most of the points. It was transitions not from O to O, but only very short range, skipping most important things. So towards completion of the project, you may think about if you need to tweak, find from ab initio or guess correct values for other parameters. And second, to be able to explain how things are working. Like what's the reason for this additional, for the shoulder in the emission spectrum? Why it is non-symmetric and why it is shifted to the, from the 1.9 transition. Make sense?
Yeah, it does.
So any quick questions right now?
For now, no.
Okay, then you can stop sharing and I will talk to the next one. Yeah, thank you. Adam, would you like to let Ellison and Sibel to be in front of you?
Yeah, sure, that's all right.
Oh, thank you. Ellison, would you like to share a screen?
Yep.
Yeah, thank you. Wait. Yeah, sure. Did you generate any questions to discuss?
No, I was able to get the video all set up. Could you send me the readings that you were?
Yes, please send me a reminder because I do more promises than I can do. And okay, yeah, thank you. Okay.
For some reason, because is this one you want me to open?
Good.
It says there's an error on line 3.
Okay, we will fix it. Let me ask your permission to type in your screen. I think you already gave it to me. Thank you. Can I close this window or you can close it? I want to type something in the MATLAB.
Yeah. I think I have to.
You need to click the lock to make changes. And then it will ask your password.
Oh. Okay.
Let me check. Yes, it looks like.
There you
It wants to respond to me, but not as vivid as one would wish. Okay, maybe it delays, the signal is lost in delay. Would you please type in this command window ls, enter. Click.
go. Now it won't let me click in there either. Um, let's see. Yeah, it won't let me. Should I pause the sharing and restart it?
Yeah, that's you can stop sharing, or I will give up remote control. Maybe it will. Can you now type something in the command window?
Yep. Can you see it now?
Okay, ls, enter. You need. So you are running KL path node CHEM. What if you click run? Can you put the no, not here. Yes. So there is a little technical thing that looks strange for me. If let's go to command window and type ls once again. Can you type pwd? pwd for pathway detection. Enter. Users, Alison Schmidt, documents, MATLAB. Let's do save as. No, not here.
Oh, okay.
Save as. Downloads. Oh, okay, you are in downloads, but maybe we can just cancel, go to downloads, and everything will work right away. Cancel, click cancel. Okay, click in the command window. Type cd space dot period, enter. And repeat it once again, cd space dot enter. cd, oh yeah, okay, cd space downloads, not two periods, just down, start with uppercase. It's downloads.
Enter.
Enter. Type ls space star dot m. No, star like asterisk.
Oh.
It looks like we are NASA agents. Space and star dot and then letter M, period, letter M, enter. Okay, so you have KL path node final warm up. Okay, and did you download here the, oh, okay, let's do ls space space star dot txt. Enter. So I didn't send to you this cesium PB bromide log pod. If I didn't, I need to complement it. I thought we are just in the wrong directory.
You want me to open up the email you sent me?
Yeah, if you show it, but I'll try to send it, resend the right file right away.
I've got a bunch of them, but I'm not, because I have 3 or 4.
Yes, you have it. You need to download it.
Which one is it?
This that is selected. CSPB.
This one?
Download. And now let's go to command window of the MATLAB.
Okay.
Now click on the run. Just run. Okay. Press any key.
Okay, there we go.
So something is working, right?
Yeah, it's working.
Yeah. So there are 3 segments in your data. So the central segment from approximately 35 to 60 corresponds to semiconducting layer of flat halide perovskite, which is very popular in scientific research right now.
Yep.
The object at approximately 70, you can point it by mouse so that I see that you've followed what we're discussing. Yes, it corresponds to the, I think the acceptor, the titanium dioxide layer that accepts electrons.
Yeah, I was just reading about it. The lights and I think it's titanium dioxide, something like that.
Correct, absolutely perfect, yes. And the little feature at around 15, for x equals 15, can you move up? Yes, it is a dye that either donates electrons or soaks the holes.
Yep.
And, instead of typical 2-component layers for dye-sensitized solar cell, here is 3 components. So light is absorbed in the central photoactive semiconductor lead halide perovskite, and then electron goes to titanium dioxide, and hole goes to the dye.
Yeah, it's really interesting.
Okay. So this image that you see, let me approach Wyatt and ask his opinion on this image, because we were discussing something and he may share some. Let's just tell something. What do you think about this figure?
The different energy levels.
Yes. So tell more. Like there is a potential, right, which is the same as for dynamics, and then there are several horizontal lines with patterns. What they are and how they are obtained. Just it's similar procedure. Just explain what
I'd say that so at the base level, it's there aren't as many drastic changes. It's more smooth and continuous. But then once you start increasing energy levels and getting either, I mean, in mine, it'll be kinks in either the bonds or different angles of the bonds that aren't necessarily as natural. You'll get different changes that will affect how the electrons will interact with everything, and then you won't have such a continuous line. You'll have more of a separation into 2 or into 3, depending on.
Okay. And how these lines were obtained?
By plotting the.
Before plotting.
Oh.
So by Eig, right? Finding eigenvalues.
Finding eigenvalues
of Hamiltonian.
Yep.
Okay. Yeah. Thank you much, Wade. Ellison, does it make sense?
Yeah.
So I'll try to ask your permission to do something on your screen, and if it doesn't work, I will ask you to do something.
Yeah, let's see if this will work here.
Okay. So I want to pull.
There you go.
Okay. So we can select. So this blue line, which is identical to the one we saw during the dynamics. Let's put them aside. So the green line on the dynamics figure and blue line in the eigenstates figure are the same, right?
Yep.
So they show potential. Where potential is lower, electron has higher probability to reside. Where it is higher, it has less probability to reside.
Okay.
And finding eigenvalues of Hamiltonian, we find orbitals, right? Starting from lower energy and then higher and higher. And it is interesting that some orbitals have maxima only on the central perovskite area, right?
Yep.
And some are specifically localized on the titanium dioxide layer. So it would be of high relevance to semiconductor industry to look for probability of electron jumping from the orbital that I'm trying to point right now.
Mm-hmm.
Count what is the number, like 1, 2, 3, 4, 5, 6, 7, from orbital 7 to orbital 6, which is localized on titanium dioxide. And to design any tools to describe this procedure. Does it make sense?
Yeah, that makes sense.
Okay. So let's see. The code is inherited from one of the students who did it in the past, but to my memory, there are objective challenges, and let's discuss and then make a quick plan what to do. I'm looking for the drive marker. So if both mistake number 7 are eigenstates, if they're eigenstates of Hamiltonian, then there is no reason for system to transfer from one state to another, right?
Yep.
States are assumed to live forever. So there are 3 ways to facilitate the transfer. First, create initial state as a superposition that will be not literally an eigenstate, but will consist of several eigenstates. Second one, to model thermal activation. And third one is to apply electric field, which will break the orthogonality and facilitate transfer from one orbital to another one. I think that electric field, well, you're free to modify things. I'm just bringing up options, but electric field will be most novel and important for semiconductor industry.
Yep.
Okay, so what we can do in this code is to first, I will use first, second, and third, like identify the observable, which would be maybe probability of electron residing in the area of titanium dioxide.
Okay.
It is already programmed. We will identify portion of the code. So left and right. So it's likely to be PL3 of time variable. And likely in the present version as the code is running, the now I'm focusing on the left part. So we do not see substantial probability above this titanium dioxide area, right?
Mhm.
It is because there are objective challenges. First, electron needs to overcome this barrier between between these two molecular pieces, and second, that those are different orthogonal eigenstates. So if we would modify if you would apply electric field, the transfer to titanium dioxide should be substantially facilitated. So let's look into the script. Would you please bring up the text of the code?
I might exit these.
Keep this one. Keep this one. We may need it. Oh, if you click here, it will bring up. May bring no.
Here you go.
Okay, so I hope this script already has implementation of electric field, and if it is, or maybe other version of the script, or maybe we can just quickly add the electric field here. So I was too quick. So the potential is inserted into variable log pod.
Okay.
And in the next lines, it should be funneled from the variable log pod into the variable v, which is for potential. So you see v is read as a second column of the file log pod, divided by 27 to convert from electron volts to atomic units. And later on, let's see if it is used as is, or there is an electric field treatment. No. So I'm going to the place where the Hamiltonian is defined. Ham2 has potential as is, and Ham3 also has potential as is. Okay, so it looks like field is not inserted yet, but we can go to the beginning and do the following. V equals V minus value of electric field, and we can start with something non-ambitious, small value times x. Oh, x is not defined yet, right? We had too early at the beginning. So let's let me copy this. No, x is already read. Yes.
Yeah, I
That
think
is enough. So this is electric field. Electric field. Now let's save under different name. Does it allow us to do saving? Maybe if I'll stop accessing, it will. I give up remote control. Save under different name. Save as. Yeah, now it follows your commands. And call it maybe warm up, and before dot, after warm up and dot, click before dot. Type maybe underscore E for the field 001. E for the field 001. Okay.
E0.
Okay. Enter. Save. And now let's run. Let's just run. So I think it funnels image to one of the figures. Please bring the latest figure to up so that we can look on it. The figure from MATLAB. Click
I
on
need
the
to type that in.
MATLAB. See, it has several. It should have several windows. Or maybe do L. No. Okay, then if nothing pops up, just click Enter and see what happens. Busy. I'm requesting remote control.
Okay.
It is just a little, thank you. Just a little thing, it doesn't Control C. Oh, it is not very happy to follow my request. First type, oh yes, Control C, good. Open a figure. I want to look on the figure and the command window at the same time. And now in the command window or here, I just click Run.
Oh, there it is.
Focus on the figure. So now I click space. What we should look at, there is a line far left and far right. Before they were equal, right?
Yeah.
And now we have a little slope from left to the right, which kind of helping electron to go downhill from left to the right.
Yeah.
And when the simulation ends, when it stops, there should be the probability to form the product. And this one, there will be more figures. Yes, this one.
Yep.
So I'm going to erase the top lines because they kind of block vision. Okay, so you are coming to productive stage of your research. Let me suggest you an algorithm of activity, which you are welcome to accept or reject, but it's something that you can just follow. So are you ready?
Yep.
So in the line 8 of the code, change the number of the electric field, which is right now is equal 0.001. You can scan like 0.002, 0.003, or you can do non-linear. Then save and save and run. And after each run, make a screenshot of that.
Probably.
And then not all of these figures will go into your final report, but it will be your body of your scientific research.
Yep.
What do we expect to see? As you increase the field, blue line will grow more and more vivid. Right now it reaches the value 0.02.
Yep.
You increase field, it is expected to reach the value of like 0.03, 0.05.
Yeah.
You will have an effect of electric field controlling electron transfer.
Yep.
So please do not fear creating too many data points. If you do if you rerun it 20 times and put 20 figures analogous to this one into PowerPoint or Microsoft Word, it will be your data which we will analyze later towards your report.
Sounds good.
So I think you are ready to go.
Yep.
And I would be very happy to communicate by email or setting additional Zoom meetings if needed.
Sounds good.
Any questions?
I don't think so.
Thank you much.
Thank you.
For sharing. Okay. Sibel, would you like to share screen?
Wait a minute. Sure. Screen.
Did I share recordings of today's lecture or not yet?
Not yet, because I
Not yet.
was trying to access the recording, but I couldn't.
I was speaking intentionally something for you. Let me just to save time request control if you agree. Sibel, may I ask which computer do you use? Is it like laptop or desktop?
Laptop.
Okay, so we will try to do something right now, but be prepared. Your project is mostly numerically demanding, and
Yes.
it could be too much of resources from laptop. So running on a desktop will be better. Or if desktop doesn't work, I'll show you how to run it on.
Yeah, because I tried running the code on my laptop, and it was just crashing.
Yeah, it is quite challenging numerically, and we'll find a bypass, a way to get over it. At least I can. There is a last resort running MATLAB on the high performance computer cluster of the university. So even if nothing helps, it will work. From my laptop, it also was given hard time and heating up to like 100 degrees and blowing.
Yes.
So it's challenging. So maybe before we go into the code, would you please open the notes from today's lecture? I will personally repeat what we did.
Okay, hold on. No. Oops. Wait. It's hard to. Okay, let me look. Okay, I can move this finally. Okay, let me open my mail. Okay. So today's lecture. Okay.
Okay, let's download. So because movie may not work in this.
Yeah. Downloads.
Okay. Did the enable editing work? Or it's still thinking? Oh, okay. And now let's just run the show. Go to presentation mode.
Okay. Presentation mode.
Okay, flip forward. Yeah, please run this movie. Let's check if, okay. So I don't know if it is ideal project for, and if it is what your group is running right now. Can you run it once again?
Yes.
And would you please explain what do you see? Like
So
start, maybe run and stop. So or move this bar to the very beginning to see the initial configuration. Yeah. So can you please explain what is going on?
So we have our porphyrin ring bound to the ion, and then we have the oxygen that is that gets connected, and basically, from what I understand, the numbers shows us the density of the bond angle.
No, distance.
The distance, sorry, yeah.
Okay, before we get to details about distances, did you took organic or not organic, inorganic chemistry, or maybe you are taking it?
I haven't taken organic yet.
You haven't?
No.
Did you have elements of inorganic in your freshman chemistry?
Yes.
Okay, so what is the typical coordination of iron to nitrogens? How many iron to nitrogen bonds iron likes to make?
Typically iron to nitrogen, they make, if I remember correctly, they'll make at least like, wait, one bond. Like
No. Let's,
4 ions bonded to one ion, 4 nitrogen bonded to one ion, sorry. Right?
The letters, the word starts with letter O.
With letter O.
So with your mouse, can you please focus on show the iron, and
Yeah.
now show all nitrogens that are close to it.
Here.
Second, what else?
Wait.
Third,
Yeah.
fourth, fifth.
Yeah.
The one from the bottom.
Yeah.
6. So if there are 6 bonds together, what is the right on the equal angles? What is the right word to describe this orientation or this coordination?
It's not an octet, since
Yes,
it's not,
octahedral, right?
yeah.
Wyatt would confirm. Joshua, confirm. Adam, do you confirm that it is octahedral coordination?
Looks like it, yeah.
Okay. So octahedral coordination. So your iron is connected to 4 nitrogens intrinsic to porphyrin ring, 1 nitrogen from this pyridine or pyridine-like stuff from the bottom, and then on the top, iron can form and remove binding to any active agent. So to my understanding of what is going on in your group, it is a part of an enzyme.
Mm-hmm. Yeah.
So what is the molecule NO, which is connected to iron by nitrogen?
The molecule?
Yeah, like on the top of hydrogen, there is iron, there is NO on the very top, directly up from iron. Now move your mouse to the left.
The left.
Left.
Okay, found it.
So NO, nitrogen, oxygen. What is it? What is it?
Is hold on, what do you mean what it is? Like it's nitrogen, oxygen.
If you go to Wikipedia, what would we learn about nitrogen monoxide?
Oh, it's basically gas, and basically
what would happen to me?
radical.
What would happen to me if I inhale this gas?
Basically, I think it's toxic, right? So
it's not as toxic. It was one of the first agents used in surgery for anesthesia.
yeah.
So I recently got through dentist procedure, and he told like it is not so serious to make you full anesthesia, but a little harder than regular numbness. And like, would you like to inhale nitrogen monoxide? And I was reading about it for teaching classes, and yeah, I should try it. And one feels like
Nitrous
after.
oxide was used for anesthesia, though.
Huh?
I thought nitrous oxide was used for anesthesia.
You found it?
No, I mean, I thought nitrous oxide was used for anesthesia.
Yes. Some people start laughing, so it makes you high. Okay, and also it has some in small concentrations. It has some biological effect to cardio activity, mostly positive than negative. And this iron complex, which is in the center of enzyme, can capture and control concentration of this nitrous oxide in the body. But now we are looking from the reaction how to remove this nitrous oxide from the body on a catalyst. So if an O molecule and OH molecule would meet each other in a solvent, they may not react. But since an O is semi-bound to iron, the reaction of connecting, merging an O and OH can go with lower activation barrier. So can you focus your mouse on the OH group to the right?
Yeah.
Yes. So it is OH from the solvent.
Yes.
By thermal motion, it just hits this NO group, and we hope that it will form nitrous acid.
Yeah.
HNO2,
Mm-hmm.
which is not as strong as nitrous, not NH3, but NO2, and depart from iron, letting the catalyst. So this, let's run the simulation. And okay, so it is formation. Oh, you can just pull the bar in the middle of further, a little further. Okay, yeah, about here. So we form the HNO2 molecule, and it departs from iron. So iron is not as much connected to this nitrogen anymore, and the catalyst, iron in the catalyst, becomes 5 coordinated instead of 6 coordinated. So after this nitrous oxide departs, your porphyrin catalyst will be able to participate in some other useful activity.
Mm-hmm.
So since it is under coordinated, it's typically more active than any other chemicals. Therefore, it's going to be. Now, let's go to the next slide. Since it was prepared on Mac, it gives some crazy stuff. It rotates images. Would you please click the top left image and rotate it by 90 degrees so that we can read the axis? Or exit presentation mode and go to editing mode. Like escape to exit. Yeah, click on this image and rotate it. You see there is a little, oh, let me do it. Here is a little,
Oh, okay.
rotation. But you can fine tune it to higher quality. Let me try doing it, rotating more. And making it to fit the size. So we do show in this image the energy of the overall molecular system as far as reaction goes through. So it's like potential, total potential energy.
Yeah, over time.
Huh?
I'm saying total potential energy over time.
Yes, because the reaction goes over time.
Yeah.
But simultaneously with, and you see that it is high, then low, then it goes to a little barrier, and then it gets low again, right?
Yeah.
So here at the last time it goes down. Another image that I'm manipulating right now shows the distances that one can see on these movies over time. So
Yes.
originally, the distance between oxygen and nitrogen is big, and distance between iron and nitrogen is not changing, right?
Yeah.
This part. And as we go closer, the oxygen bumps into nitrogen. It gives additional energy to this nitrogen, and nitrogen starts departing from iron.
Yeah.
And then it goes simultaneous coherent motion and it departs. So this information of total energy
Yeah.
distance to iron and distance to oxygen can be tabulated, right?
Yes.
Then placed into the MATLAB by through this line. Dashed line is our trajectory. You recognize it, right?
Yes.
And the color means height of the energy. So we can there is a procedure. We can discuss it later. I just want to speed up to reconstruct overall potential energy map as function of these two distances.
Okay.
Then we do have two options. One option is to run molecular dynamics by just following distances, these two molecular distances, and by Newton's equation, looking if reaction will go through.
Yeah.
Product, or we can run quantum dynamics and see how the wave packet will evolve.
Yeah.
So this two-dimensional wave packet is a really cool and interesting thing. So you see there appears fringes, which
Yes.
means, but this time is in atomic units, which is a small fraction of femtosecond. So it would take a very long time until it gets to the end point.
Yeah.
So if we can cooperate and complete this quantum part, it will be cool, but it is quite a challenge for any computational equipment. So it is like holy grail or whatever ultimate goal that we can try, but we need a backup plan. And the classical trajectory is something that we can do anytime, and it is like millions times cheaper. Make sense?
Yes.
Okay, so let's go back to your MATLAB. So yes, let's click on exactly this one. The file trajectory is what we just discussed.
Yes.
So it has
The total energy and the bond distance between our iron and nitrogen and oxygen and nitrogen.
and the numbers are so low, like minus 560, because it is energy of all ions in this. But if you compare the numbers, they differ from each other, not so substantially. They like so this code WP2D reaction is quantum calculation, which and this is the movie that you were playing just in your slides. This code will kill any computer, so we should try running it, but with care. Let's go to simplest part first. Simplest part is the this force field dynamics, and I think check. Yes, we can run it without quantum part.
Okay.
Let me suggest we discuss this classical trajectory part, try to run it, and then leave the quantum part as we'll try to to make sure you can do it, but let's make the backup plan first. There is a little thing I want to. Okay, I temporarily comment this one out because the variable triple V comes from the, or maybe we can copy paste this triple V from there and then it will be full operational. So no, it's too many things.
Okay, triple V.
Triple V, it is defined right here, but to make it operational, one also needs to define this x of j and y of I. Maybe we can quickly do it. It's not a big deal. Paste. And we need this x and y, uppercase x, uppercase y. And for them, we need a number of points. Okay. Copy. Paste. Dx is defined, and we can do npts equals whatever 85 to be consistent with other code. Okay, so save and run. Oh, it also needs a mass.
Yeah.
You see from the, so it's I was doing quantum first and classical second after suffering and
Mass is here. It's 18636. Yeah.
So the quantum code uses atomic units where mass of electron is 1.
Yeah.
Mass of proton is about 2000. And if you have OH group, then mass of proton times 16 for oxygen and 1 for additional hydrogen, right?
Hydrogen, yeah.
And the value of mass changes our definition of momentum and kinetic energy and affects results. So save and run. Okay, this is something I can really, I hope I can fix, or we can copy paste from there. It was something like v equals zeros.
Yeah. Zeros, right?
Yes, this one.
Yep.
Copy. And somewhere here, just before we can paste. Paste and save. Let's try once again. Index position 1. Ah, okay. There is another cycle. So from physical chemistry lab, it becomes a programming club. Okay. And then at the end of the cycle, we need to finish it. And save and run.
Okay, yeah.
Okay. So what we do see here that instead of going this straight dashed line, it
Yeah.
makes some complicated curve, but finally it gets to the product. So it would correspond in your PowerPoint that the nitrous acid will stay additional like 100 femtoseconds near iron and move forwards and backwards and then finally depart.
Yeah.
Why we see this difference? Because here we approximate molecule with like 50 atoms just by 2 nuclear degrees of freedom, which is approximation on one hand. On another, here in classical approach, we do not have quantum tunneling, and therefore it takes longer time. But final qualitative outcome is favorable.
Yeah.
Let's bring back this little thing, and now it will be more colorful. So it brings potential, and one can
Rotate, and we can see.
see this potential.
Yeah.
And you see this black line explores different places of potential surface and finally gets through.
Mhm.
So if we have, like if we fail to do quantum dynamics in time, what one can do here, how one can explore this code further. So one can change initial conditions.
Yeah.
And see what happens. So like instead of 4.7, one can start from like 5.7.
Yeah.
And here I want to do the line with different color, maybe red.
Mhm.
Save, run. And with different initial condition, it doesn't get through in the same time. It makes another trajectory. Right now there is no visualization, so it bumps into wall across, then reflects, goes back, and moves there. But if we set up the simulation time long enough, so tau is time step, and the yes. So if you set number of steps is n tau, if we explore it for longer time, maybe reaction has chance to get through. Yeah, see it,
Yeah.
it goes through. So there is a way to make a movie how the little point goes across.
Okay.
It could be done later, but you see, you can modify the initial position and also initial momentum.
Yeah.
And see what happens. Sometimes it will go wildly. Sometimes you will see something interesting, but those are basically your input parameters that you can, like, if quantum will not work, you can do maybe 10 or 20 different runs and report how you see reaction is going through.
Okay.
And just make images for separate runs. Make
Okay.
sense?
Makes sense.
Okay. So now you have a backup plan.
Yeah.
Now let's try to torture your computer.
Exactly. Oh my God. I tried running it. It was just not going.
Okay, then let's.
So do you want us to schedule like a, I don't know, a meeting, and so that we could like use the computer in a lab or something?
Okay. Which time are you in your lab? Do you like come to the research lab often?
To my own research lab.
No?
Well, since we're packing, I don't go there really, since we're like getting ready to move. So we're just basically everything is packed.
Let me try to show. No, I need to make some preparations, but please let's set up a meeting during maybe Thursday or Friday.
Okay, yeah, Thursday or Friday would work.
Thursday is better.
Okay.
And remind me, we want to run this code on the HPC cluster.
Okay.
CCAST HPC cluster, and then it will be independent of your equipment.
Okay, sounds good.
So, and if it fails, let me show most important equations that are unique for your project because no one else does quantum classical dynamics. So, did you have college physics or physics in high school?
Yeah.
Okay. So, what do you think about Newton equation of motion?
It's useful and it tells us.
Okay, so it doesn't scare you, right?
No.
So force is a derivative of potential.
Yeah.
So you subtract values of potential in different points, and you get force.
Mhm.
Now increment in position comes from constant velocity.
Yeah.
And velocity is momentum divided by mass times
Yep.
time.
Mhm.
V times dt plus acceleration, which is acceleration
Divided by mass.
divided by half and times delta t squared, right?
Yes.
And then here is we update the position, right?
Mhm.
And here we accumulate position into variable.
Mhm.
Accumulate into a variable. So in case we fail, I hope not, but in case we fail a quantum calculation, you may need to convert this coding into like equations in Microsoft editor and then present in your report and presentation.
Okay.
Any questions right now?
No, not really. Well, I have a question. So would you want us to meet tomorrow then?
Yes, yes.
Okay. What time would work for you? Because I'm available like after I have classes till 12. So after 12 I'm free.
Let's tentatively plan for 5, but with
Okay.
usual confirmations by emails.
Okay. So let's plan for. Okay. I'll send you and I'll email you then.
Okay. Anything else for now?
That's all. I'll still keep on working and playing around with the.
Yeah, maybe just as a backup, accumulate several trajectories.
Yeah.
Be confident that you succeed in any way. Okay, then you can stop sharing.
Okay. Thank you.
Adam, I think it is your turn.
All right.
Okay.
Let me share. Yeah. Here's my.
I think it wants you to press any key, right?
Ah. Oh.
Like space button. Oh yes, it goes forward.
Mhm.
Yeah, even if everything goes well, it requires some patience. Did you Oh, I see. You didn't modify DE off, right? You just use the values that were provided originally, correct?
Yeah, yeah.
So let's wait until code is finishing and we'll give probability of transferring from blue to red or whatever transfer probability, and then discuss how to interpret, modify, and what to do next. If I do this trick, which you just did on my computer, it will complain to me. It tells like size of the image is changed. I cannot record video anymore.
Oh no.
But let's look on your other figure that is behind this, raid by Marcus. Okay, this one is implementation of the Marcus formula that I hope you were studying in your, no, the y-axis is wrong. But the calculation here is, and both x-axis and y-axis are wrong.
But yeah, it's I mean it describes like I guess basically what I saw on Wikipedia. You know, this
Yes, yes. So what is lambda in this Wikipedia?
Lambda is the reorganization.
Okay.
It's yeah, it's just the I guess it's essentially the energy that's required to push all products over or I'm sorry, all reactants over to products or all reactant nuclei to their product position without the exchange of electron, I believe.
Okay, and what is reorganizing? Why it is called reorganization?
I believe it's just maybe.
Your Wikipedia tells it.
Oh, does it?
Yeah, you're right. Slowly move your mouse lower.
Electronic coupling.
Stop.
Wait. Oh, is it just
Next in the brackets.
Oh, solvent reorganization.
So can you explain your understanding what is solvent reorganization?
Solvent reorganization would just be man, I guess just solvent molecules, man, like moving around the nuclei.
Yeah, let's scroll if this Wikipedia gives images. If not, we will draw an image together or find it in better Wikipedia.
Does it have to do with not necessarily solvent, but
solvent
like
is very good. There is another internal reorganization and solvent reorganization, but typically it's a good article, but it is not very like popular science. Let me, with your permission, open another page and type maybe okay, Marcus theory, solvent reorganization, and then I will play lazy person who is lazy to read. So just click on images. Yes. So can you yeah, just copy paste this image and paste in your PowerPoint. paste from Clipboard.
There.
Okay, so tell me what you see and what is solvent reorganization.
It looks like it looks like it's being used to describe the state. Oh, so like the solvation of whatever compound it is, like the like giving of charge.
So your electron transfer is when electron goes from donor to acceptor. In the ground state,
Yeah.
donor is 0, acceptor is 0. In your excited state, donor is plus, acceptor is minus, right?
Yeah.
Now, let's look on the lower schematic diagram of this salvation shell. What can you tell about pluses and minuses of the in this little ellipsoids? Are they order or they are random?
They're not unidirectional, so the no charges are coordinated to either donor or acceptor.
Okay,
and
yeah, this is intermediate, and if you look on the product, the third image.
Yeah, it looks like the charges are coordinated how we would expect.
So minuses of the polar solvent
Yeah.
are oriented towards donor plus, and pluses of the acceptor charged acceptor minus charged positive parts of the solvent molecules are oriented towards acceptor, right?
Yeah.
So upon charge transfer from donor to acceptor, solvent molecules rotate.
Yeah.
And it
So
takes energy to make them to rotate from one configuration to another one.
I see.
So the energy
Okay,
needed to rotate them is reorganizing solvent molecules and called reorganization energy. Make sense?
Yeah, makes sense.
Okay, let's go back to your MATLAB. Joshua, did you generate a question? Or you're I'm just checking because or you're planning to depart. Okay, I just saw some motion and with my side vision. Okay.
So this would be lambda in notation.
I'm not sure. I'm not sure. We will figure it out together.
Okay.
I don't want to lie. I better say I don't know. Let's scroll through your what it is. There should be several MATLAB figures. So this figure with the word yield is our main workhorse.
Yes.
So if you have no ideas, or even if you have ideas, but you want to accumulate constructive, useful data, productive data towards your project, rerun the code with different parameters and just copy paste this top panel in a graphical form. Okay. Later on, we can analyze it, or we can find a better way to discuss it. But as a backup plan, maybe run code several times and like 20, and save 20 versions of this yield figure.
Okay.
You remember as we were discussing with Ellison.
Yeah.
Now, what can you productively change? Suppose you are going to run the code 20 times. I would change this DE off in the range, maybe from minus 0.0001 to plus 0.1, or if you are maybe in a little broader range, something like that. So split this range onto equal amounts, plug them into here, and rerun and save the yield figure.
All right.
If you have this data in your PowerPoint, then you are safe, and one can always process it. Also,
So
rate, you can also make a table. So in one column, you put the value of energy offset. In another column, you do this rate value.
okay.
So it will be an analysis. Now, I apologize for speaking too much. It will be much, I would prefer just to make it as a little interview, but I'm just trying to save time. Let's figure out what is this figure 1, and can we redo it? So I select the arrow, select the image, double click. And see what happens.
Ah. One moment.
So there should be an option to convert it from linear to logarithmic to log scale. If you cannot do it in the mouse operated thing, we will do it. So we need which axis? We need y axis. Core style axis line.
I've been released.
Too complicated. Maybe your brain is much brighter than mine, and you later figure out how to do it. But I'll go through old-fashioned and just identify where it is done. So in this range, it basically does. Oh, here is a definition of lambda. So it's difference of this distances squared and times the rigidity constant. And here, basically, it does same thing as I was suggesting you to do. It sends energy offset, and then you see it implements Marcus formula directly. It uses lambda and this energy offset, right?
Yeah.
So redo this thing in the log 10 of Marcus. It will be a little quicker than finding a way to copy new figure, figure. And now I just paste this. So now let's go into, remember before it was like a Gaussian shape.
Yeah.
And if you do the same thing in the log version, it shows a parabola.
Okay.
Because Gaussian is just exponential of a parabola.
Yes, yeah.
And log of Gaussian will be a parabola.
Yeah.
Okay. Now let's go back to your wiki. No, not this one. Your Wikipedia. So would you please, yes. So let's scroll through this stuff. Yes, yes. I think this curve is what Marcus got his Nobel Prize for.
Yeah.
This is what is y-axis?
Y is the logarithm of the rate. So
Log of the rate. Does this curve look similar to parabola?
there, yes. I was thinking that when I saw it.
Not perfectly, but similar, right?
Yeah. Oh, very. Yeah.
Okay.
So,
And what is x-axis?
XS is that's the delta G naught.
So it's energy offset, right?
Yes. Yeah. Yeah.
So what is important? Each point on this curve corresponds to different molecule. It's not like we are scanning regimes for one molecule.
Yeah.
If you're playing with different energy offset, it means like you are looking on a range of molecules, each of which fitting different energy offset between donor and acceptor. But it is so universal law that it will work for basically any molecule where charge transfer is happening.
Yeah.
Therefore, it's worth of a price.
Yeah, that makes sense.
Your goal would be to make like this curve is coming from just programming the Marcus formula. So it's Marcus formula. He already got a credit. Now we need Fleisch's formula to compete with Marcus, or at least numerical data. Right?
Yeah.
So when you will redo different values of energy offset, and you will save the rate and save this image, you will see that slope of the yield, which is equal to the rate, is expected to approximately fit this curve. Maybe you will get it, maybe you will not. It is a little challenge. Maybe you'll find that Marcus failed and everyone else in the world was collecting wrong data. Or maybe you'll find that quantum theory and physical chemistry class contradicts with Nobel Prize and therefore everything is wrong. Or maybe you'll find that in some energy range they agree, in others they diverge. So
Makes sense.
You're coming to the unknown area, like terra incognita. And I'm really curious to see how your data points will fit or agree and disagree with this reference point.
Okay.
Do you have a vision how to go forward?
Yeah, I think so.
Okay.
Would you recommend hide that? Would you recommend changing this value and this value at the same time? Just
Changing only energy, it looks like simple, but if you do it 20 points and maybe there is a chance. No, I wanted to go to a different MATLAB image. Just a second. There is a chance that by putting the data on this image, you'll see that they will show big fluctuations, big error bar. And then maybe it will spark your interest as a researcher to redo some data with finer points. And then doing, instead of like 20, doing 40 runs, it will already exhaust you. So I appreciate your intention to explore all parameters, but let's do, you do whatever you like and find scientifically interesting as a creative person. But maybe making a simplest backup plan B first is a reasonable. And then if you get something, you get this curve, agreeing or disagreeing. I make a hypothesis that there will be oscillations. When there is a vibronic resonance, it will be a little higher. When it will be vibronic off resonance, it will be a little lower. So it will be not continuous line, but going up and down, up and down. But I don't know. It's like your project, and you may do some discovery that will surprise all of us. But after you do this first curve, if you find it really cool, you can try some other creative things.
Okay. Yeah, I'll do that.
Okay. So suggested activity is to like run about 20 times, collect data, and have them ready by Monday.
Okay. Check.
Whew. Any questions you wanted to ask?
No, I don't believe so. I'm just I'm just gonna deliver this theory. I'm not gonna focus on a specific molecule or a specific complex.
Exactly. So it's you're in preferential unique situation. Everyone else studies specific molecule, and you are doing theory of everything.
Okay, that's good. That's good. I like that. Like
Okay.
it's fun to learn.
And on one hand, it is cool. On another hand, it is a little less work, because if you try to find parameters that would fit your specific molecule, it will be like results will be not more impressive, but it will be more meticulous work.
That makes sense.
Which you're welcome to try, but maybe after this basic thing, which can be also interesting by its own.
Yeah, I won't waste too much time before I've this done.
Okay. So are we done?
Yes, I think so.
Then you can stop sharing.
Okay.
And I will check again one-to-one if there are questions before we adjourn. So I'll check those who are in class and then return to the stage.
These are messy. But so what you mentioned, multiplying by a factor.
Factor 0.1, and then it will, yes.
Okay.
Keeping like the when you plot it here, like plus EE, but before plus this real side times 0.1 plus EE.
Almost okay. There.
And then yes, it will put the same scale, but it will be more aesthetic. So it will keep the same. Yeah. All good.
No questions for now. But in terms of the, I'll send you an email already to Monday.
Okay, so try to collect data and make a plan of your presentation before Monday, so that you can. Of course, we will have the makeup lab on Monday evening, but if you find some questions, give me a heads up so that I can prepare and start thinking how to answer during the weekend or like on Thursday.
All right.
Okay. No more questions? Okay, yeah, then feel free to leave.
Do you adjust this too? Or
No. This is kind of objective information, the depth of the potential.
Okay.
And this is just the way how we.
It's easier to see
Mhm.
that way. Okay.
Correct. Sibel, do we need to talk more today? Are there any questions you wanted to ask, or?
No, I guess we'll talk more tomorrow. I'll like send you an email right now.
Please send me a reminder. I
Okay.
intend and want to meet at 5, but I can just open emails and find some additional tasks, and I apologize ahead. I may forget things. If I get a reminder, it will be really cool.
Yes, I'll send you a reminder tomorrow. Around noon.
Thanks so much.
You're welcome. Thank you.
Thank you. If you feel free to disconnect.
Okay, sounds good. Thank you.
Laura, do you have more questions?
I don't know if you have some time. It's just research question.
Oh, about your RRR, about Redfield dynamics?
Yep.
Great. Yeah, thank you. And Adam has the, okay, yeah, let's chat and share screen if needed.
Okay.
So this image shows the homoluma gap is 0 or close to 0. Is it right?
So when you say close to 0, you're talking about here, right?
Yes. Let's open. Let's if you have MATLAB open, let's come to. Please bring. Are you sharing one window or the whole display?
Let me show you whole display. So I should pull up the script itself. Is that what you want me to do?
Oh, just command window would be great. If you bring command window where you generated this figure, I can figure some things from there.
But I need to open up the code itself, right?
Command window. Okay, good.
Here. Yes, here.
Okay. And I want to see command window so that we can run it there. Okay, so let's type request control. Yeah, thank you. And non-radiative dynamics, LS. So your version of the code is for master equation 11b. Okay, just in case I am going to open new figure. Okay. It shows only one new figure. That's okay, but
More than one.
it's okay. We'll figure out everything. So
I think it's the radiative that gives more than one.
no more. Interesting. Comma 97. I will quickly answer.
Sure.
С phone. Алло. Ой, я думал только 7. Нет, сейчас пойду. Мы с Вовой быстренько ее проект обсуждаем, но я уже всех распустил. Хорошо. Ну все, пока. Your boss is calling me and telling me like it's 1 hour past the end of the lab.
Yeah, it is. That's why I keep saying that, like, are you sure you have some time when you need to go?
Once again. E, E, H. Starts from 0. Okay. Let's go to the beginning and check where this EE and EH are defined. I think there is a recent change that coming not from myself. Find EH. did you do density of states for this model? Is it really, it confirms that HOMO and LUMA have zero gap, but I'm a little surprised.
No, I didn't do density of states for it.
Yeah, please do density of states and linear absorption. I'm just very curious. It's not a problem if it has zero gap, but we should just
Confirm.
make sure.
But what's the implication of if the HOMO-LUMA gap is zero?
Then it can be bad emitter. Not necessarily, but typically good emitters have open gap.
Yeah, I mean, Dr. Kirina already suspected it was going to behave like this.
Okay.
So yeah, she already said she suspects it's not going to emit.
Yeah, but let's debug and make sure that everything is working on some good example that is predominantly a good emitter. So yes, this is a code only for electron dynamics. Did Aaron shared other codes?
He shared the one with the radiative dynamics.
Okay, yeah, please try running it, and if it doesn't work, I'll share analogs from my repository.
Yeah, I ran into an error with that one. That was the one I sent to you.
Okay, yeah, I'll check if it works without errors, or if I fail to do it in time, we can do it together. Do you have this code open right now?
No, I don't have it open right now, but I sent it to you with all of the input files. So
Yes,
you
thank
can your
LS. Do you have this code in this directory?
It's one step out.
Okay.
Radiative dynamics.
I'm a little stupid. Which one?
No, just hold on. Just here. Yeah, this one. Yeah.
Yes. Okay. So let's run it. And see what happens. Is it running? No.
Doesn't look like it is.
Yeah, once again, run.
I always like to close all of the previous ones because I don't know, maybe there's something wrong with my MATLAB.
Oh yes, if it shows this time, it means it runs in a productive way. It's good.
Yeah, it actually showed this time, and then it hit an error after running all this time. Something about what was it now? Oh, I don't remember. Yeah, that one. Mesh.
Okay.
Something. Yeah, I came up with two figures. There's another one with like the orange. Yeah, this one and yellow.
Okay.
I never saw this one.
Okay. I will. We may try to find everything right now. So
Follow 3.
and
Yeah, that one. Mesh log time T1. I don't know, maybe there's something
Wait, 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 wait. Just Great. Copy. Figure. Paste.
So there is something wrong with
Why,
ID.
why it tries to correct me? Is there? This version of MATLAB thinks that it's smarter than myself. Emission. Oh, okay. We. I see. I see. Let's skip this line. So we need to compute and then plot. Copy. Paste. Enter. Last figure. Another figure. So very interesting that emission is negative. It's something strange. It should be positive, but okay.
That was the same thing that happened with using Gaussian. And we're trying to calculate the triplet. Yeah, triplet. The energies and frequencies were negative.
Okay. Okay, so it has emission at 2 electron volts, at 1 electron volt, at yeah, so it's good. It has emission. It just was not seen because it's a little bit less intense.
But it was still under negative, right?
Pardon me?
It still shows negative, right?
Yes, but we'll figure it out. It can be just someone made an error with the sign. From 0 to 4, and then we get from minus. Okay, so there is an emission at 2.8, 1.8. 1.74. But you see, the emission here is less intense than this infrared emission, which so you should try to do these calculations, or we should start from the model which is a good emitter predominantly, and maybe let's. I think codes are working, and we need to discuss the physics, the mechanism, what is the system and why it is emitting. So next time when we talk, maybe show the image of the molecule, and just discuss the molecule itself. And density of states, just background information.
Okay, but wait, like according to this figure in front of me, the y-axis is what? Is it emission?
Yes.
But it's showing negative. So what does that mean?
So for small numbers, log is negative.
Oh, it's a log value, right?
Okay, well, I think I need to go.
Yeah, you should. I get it now. I thought it was absolute. Now it makes sense. Thank you.
My pleasure. My pleasure. Yeah. See you around.
Yeah. Have a good night. Sorry for taking so much of your time.
Oh, not a problem.
All right. Thank you.